Hello and good morning. I'm going to give you a short lecture on strain measurement using strain gauges. So my name's James Pickering and the content of this lecture are as follows. So what is strain? Then moving on to the use of strain gauges to initially measure strain, go under the process of strain, the importance of the strain gauge, and then moving on to Wheatstone Bridge. And that'll become apparent why we need to use Wheatstone Bridge. And then some other important considerations. So going from the Wheatstone Bridge to the engineering project or system, there's some other steps that you might need to undertake. So after this lecture, I hope you'll be able to understand the following key learning points. So the use of strain gauges in the process for measuring strain, and also the Wheatstone Bridge, the use of the Wheatstone Bridge to convert a resistance from strain to a voltage that's then useful for us in engineering. So what is strain? If we're looking at this body here, we've got length and diameter, and we're subject to an axial force. What we get here is a change in the length, and this is effectively what strain is. In the case of the x-axis, defined as the change in the length over the original length. It's the amount of deformation of the body due to an applied force. So that there is when we're undergoing a positive or a tensile force. We can also undergo a negative compressive force, where you can see here the actual length of the body has decreased. It's also interesting, useful to consider the Young's modulus and also strain. So if we take the Young's modulus equation, rearrange it to make strain the subject, you can see it's stress over Young's modulus. So you can see that these both play a role in terms of the strain of the material. So as well as changing length in the x-axis, you also get change of length in the y-axis when you have compression and tension. So in the case of tension, you have here a reduction in the diameter as you would expect as you apply tension force. And quite opposite to that, as you apply a compressive force, you get an increase in the diameter. And it's described by this equation as a change in diameter over the original diameter is equal to minus, and this Poisson's ratio here, multiplied by strain in the x-axis. And this can be rearranged to give the Poisson's ratio, to make Poisson's ratio the subject, which is effectively just minus the strain in the x over the strain in the y. And typical values for steel are between 0.25 and 0.3. So how is strain measured? This is via the use of strain gauges. So strain gauges are used to measure the strain acting on a given body. So it could be the load of cars over the bridge, the loads on the aircraft wing, or a gust of wind acting on these wind turbine blades. So in terms of looking at the strain gauge, you've got the test specimen, which could be like the bridge or the aircraft. Attached to this, it will be attached via some form of adhesive to this carrier. And then here you've got this metallic grid on the strain gauge, which is formed of foil, with these being parallel to one another. So when undergoing strain, so let's just put this under a force, as we saw, so it'd be under a tension force. These little parallel foil things, they effectively are going to stretch or increase in length as they undergo strain. And then you've got the leads here for positive and negative. So the cross-sectional area of this grid here is minimized to reduce the effects from Poisson's strain, as we talked about earlier. And yeah, strain gauges, they come in various different forms. So the foil type we spoke about, you've got the wire type and the semiconductor. So foil type possibly the most commonly used in today. Various applications, so you can see here the strain gauges are attached to a bearing, some sort of connecting device here, so you can imagine a rod being attached through here and attached through here, and then the strain gauge is here to effectively monitor the changes in strain. So in terms of strain gauges, the electrical resistance when using a strain gauge varies in proportion to the amount of strain acting on the device. So if you bend or if you put it under tension or compression, the electrical resistance will increase, and it's given by this equation here, where R is equal to rho, which is the wire resistivity, multiplied by the length over area. So as you put it under tension, the length is going to increase, the area is going to decrease, the resistance is going to increase, and compression, the length is going to decrease and the area is going to increase, the resistance will decrease. Then if another important thing to look at is the gauge factor. So the gauge factor is effectively the rate of, well, the change of the resistance over the baseline resistance over strain, and typical values for this are approximately 2. And if you look at the specification of when you buy a strain gauge, it will be within there. Approximately 2 would be the value. So the importance of a strain gauge. So when we're looking at a material property of stress versus strain, and what we have here is the elastic region here. So this is effectively Young's modulus. When we get to this point here, we've got something known as the yield strength. And if we go beyond this point, beyond the point of the yield strength, we get permanent deformation or permanent destruction of the material. So really, we want to always stay within here. In history back years ago, you would put on a large safety factor to avoid getting anywhere near there. However, we can use strain gauges to effectively monitor the strain to ensure that we don't get near this point. So just a quick demo here of a bar, it's got a strain gauge attached to it, 350 ohms. It's got approximately a gauge factor of 2, and it's been put under tension and compression. And what you'll notice is under compression, you get a resistance change of -2 ohms, and under tension, you get a resistance change of 2 ohms. So it's exhibiting an electric resistance of around change of around 0.57%. So if we rearrange previously what we saw, equation 1.6, the strain subject to compression is given by this equation here. So where the change in R is -2, when we're looking at compression, K, so the gauge factor is 2, and R is 349. Okay, to note, 349 is the value that was given on the strain gauge. So 350, but 309 was, and then this is the strain value they picked up. So notice a very, very small value. And under tension, likewise, you can see that the signs just flipped as you would expect. The Wheatstone Bridge is a method of measuring small resistance changes accurately. The construction is also used to convey a change in resistance due to the force applied or load applied to the strain gauge to a voltage output. Voltage output, that's useful for measurement, and also when we move further on to control. Voltage is really what we are interested in. So the Wheatstone Bridge is constructed with 4 resistors, as you can see to the right, a voltage source and a voltage output in the connected across the center of the diamond configuration. So in the case of the top right, we've got a 5-volt voltage source, and all the resistors in the top right are all equal with 350 ohms. So if we following Kirchhoff's law and Ohm's law, the following is given. So VO, so our voltage output, is equal to Vs, which is our voltage source, multiplied by R2 over R1 plus R2 minus R3 over R3 plus R4. Therefore, the voltage output at VU here is equal to 0 when R1 over R2 and R4 is equal to R4 over R3, and the bridge is said to be balanced. So if we look at this particular example and we look at the source, so we've got a current flowing from the positive terminal from the supply voltage. What will happen is it'll split equally down here and down here. The same current then flows through R2 and R3. And if you recall Ohm's law, voltage equals current multiply resistor, we can then work out what the current is acting through there. And then also, because we know that the current is equal, because we haven't got any, because the resistors are equal and the current's equal, we know that the voltage will be 2.5 and 2.5 here, and hence there's no potential difference. So you can see VO is equal to 0, so the bridge is said to be balanced. If any of the resistor values change, the output voltage VU changes, hence VO, so the output voltage would not be equal to 0. So in this case, here you can see R4 has been replaced by R4 plus delta R4, and when subject to a tensile force, the resistance changes to a value of 352 ohms. So it's got a slight increase in terms of the resistance. Note that the change is 2 ohms, and that was the example that we looked at previously earlier. And you'll notice here, if we work out what initially I should say, there's actually no change to the current values along the left half of the branch. The increased resistance, however, on the right half branch here, so for R4, results in a drop in the current. So if you're looking here at the current, the value is actually decreased. So this is decreased, and that effectively the current is equal to 5 volts over 702. So just these two resistance here, the product of these, these two added together, which is equal to this value, so milliamps. The voltage is then determined, so it's just 5 divided by 702 multiplied by 350, and that gives us a value of 2.493 volts. So you notice now we've got actually a drop in the voltage, and we now have a potential difference of 7 millivolts. So hence the Wheatstone Bridge is converted from a resistance value from the strain gauge into a voltage value that's now useful for us in an engineering application, to use an engineering application. So we've got a voltage out from the Wheatstone Bridge. So other important considerations: the potential use of a potentiometer when the bridge is initially not balanced prior to a load being applied. The voltage output from the Wheatstone Bridge will contain noise, so possibly to filter, low pass filter, perhaps RC circuit. The voltage coming out of the Wheatstone Bridge was millivolts, and the use of an amplifier would then increase this to something which is perhaps more usable. So it could be from 0 to 5 volts. And from that 0 to 5 volts, it might be that you calibrate your device for maybe for strain or force or whatever. And if you look at the Quanza flexible link user manual, that's useful in terms of, type this into Google and you'll get the manual and have a look at how they calibrated the device for strain, so based on the voltage. Multiple strain gauges, so we looked just at one strain gauge. However, you could replace all 4 of the resistors with a variable resistor, and you have things such as effect of a temperature on the strain gauges. So there's the idea of using a dummy gauge, and then wire length also has some issues with the length of the wires and resistance. So interesting application that I'm interested in is looking at these warehouse robots, so lifting very, very large weights and transporting autonomously around. So initially to measure the mass of the goods, this can be done via using a strain gauge and going through the process that we talked about in the lecture, and also some of these other important considerations. And also this force control robotic gripper, it uses a strain gauge that's calibrated to measure force. So both very interesting, so have a look at those videos, please. I believe the following are key points to take away from the lecture. So the mathematical description for strain and how this relates to Young's modulus and Poisson's ratio. The resistance change of a strain gauge subject to tension and compression. So under tension, increased resistance, and under compression, reduced resistance. We've gone through the numerical description of the gauge factor with a typical value of approximately 2, and you can only find that in the specification when you purchase a strain gauge. And we've gone through one of the reasons as to why you would apply strain gauges, so to prevent loading beyond the yield point. We've gone through how the Wheatstone Bridge is used to convert the change in voltage through strain to a voltage output, and we've also looked at further considerations beyond that of the Wheatstone Bridge. So I hope now you've got a very good understanding in terms of the key learning points and you were able to explain those points. Thank you for listening.